This is part of Simplified revision series. We have discussed most of the core subjects. We have discussed aptitude. We have discussed electrical circuits. Now we are discussing medical imaging. That also, part 1 is done. This will complete part 2. So this is today's thing. We are looking at specifically PYQs from 4 years, 2020 to 2023. So far we have covered ultrasound, X-rays, CT, right? So we'll do MRI, radioactivity, and image formation questions today. I'll discuss bare minimal theory. You need to solve this, not just give you solutions. And we'll also look at questions in increasing orders of difficulty. So far, we have discussed ultrasound, X-rays. So this inhomogeneous case is almost coming every year, right? CT also we have done. Oh, this is PET and SPECT. PET, SPECT, radioactivity. We need to know a few basic things. First is units. 1 becquerel equals 1 per second, 1 particle per second. Then we have Curie, define it in terms of becquerels. How much is this? Get some colors. See, the contrast, such a huge difference. Curie in terms of becquerels, 0.7 into 10 power 10 is one thing. The most thing, we have n as a function of time, right? This is typically n naught. It decays, a constant of lambda. And we define activity as minus dn by dt happens to be not lambda e power minus lambda t. Then we have additional extraneous things here, like this decay constant, say t half is ln 2 by lambda. And mean life, in life, this should be equal to 1 over lambda, right? These are most of the things that you need to know regarding, radioactivity, PET and SPECT. Let's quickly go solve this. Hey, can you have the answer keys ready and just let me know the answer key so that we can quickly verify that the activity of a nucleide with decay constant of 3.2 into 10 power minus 5 second is 6 millicurie. Radioactivity of the radionuclide at 4:30 p.m. on the same day would be. So notice you can call this A naught, initial radioactivity, right? So what is given here is A is A naught e power minus lambda t. We want to make sure lambda and t are in the same unit. Initially, this is 6 millicurie. N is the number of particles, right? Number of particles per number of particles. dn by dt. So lambda is inverse of time. So this is particles per second. So this is dimensions of Curie, A naught. So we have 30 quickly, yes. In seconds, so we need to get it t in seconds. It's I suppose in the same day, 4:30 to 10:30, 11:30, 12:30, 30, 2:30, 3:30, 4:30. So 6 hours. So your A, get a better, your A initial is, and we need the answer in millicurie. So let's do millicurie into e power. Lambda is minus lambda is 3.22 into 10 power minus 5 into time would be 6. 1 hour has 60 minutes. Minute has 60 seconds. So this power is dimensionless. And the answer, I suppose, is 3 millicuries. Milli, right? This is decay constant is 3.22 10 power minus 5 into 10 power minus 5 into 6 into 60 into 60. I get this to be 2.99 up to 2 decimals, 2.99 millicurie, where I inherit the units of 6 curie. Fairly easy. How much is that? 3.22 into 10 power minus 5. 1 over that is 31,056 seconds. How many hours is this? 0.6 hours. Yeah, roughly it becomes like half. Kind of time scale makes sense. What is given is like 8.6 hours is time constant. Talking about 6 hours. Radioactive isotope nuclei are needed to produce a radioactive level of 2 millicurie. Assuming decay constant as this, atomic weight as this, Avogadro number as this, mass of n radioactive nuclide. N So here n equals a by lambda. Can get the number. So let's quickly, if you can get the number, it's kind of write it here itself. Activity is 2 into 10 power minus 3. Number of particles will be 3.7 into 10 power 10 becquerels. That's number of particles per second. So let's divide by lambda. We'll get, per second will get cancelled. 3.22 into, if you need some contrast by lambda, this is 3.22. Did I start recording this? 0.22 into 10 power minus 5 particles, the particles. So let's get this number. This number, that's essentially n, right? So many particles, number of moles would be divided by the Avogadro number 6.02 into 10 power 23 moles. These many number of moles. 1 mole is 98 grams. So these many number of moles would be into 98 grams. 98 grams. So we can calculate what this is. So we know n. N is this whole term. If you're like slightly confused, is that whole thing. N is this whole term divided by Avogadro number into 98. Let's find out how much this is. 2 into 10 power minus 3 into 3.7 into 10 power 10 divided by 3.22 divided by 10 power minus 5 into 98 divided by 6.02 divided by 10 power 23. I hope I entered all of them correctly. How much are you getting? Nano, I'm getting 374 picograms. If I enter the numbers correctly, 374 picograms. 3.14 into 10 power minus 10. So this is where you need this, what I recall initially, 1 curie is 3.7 into 10 power 10 becquerels. That is decays per second, right? You need that. Yeah. This question, consider two radionuclides P and Q. Half-life P is 4 times half-life of Q. And T equals 0, there are N atoms on both radionuclei. When will the radioactivity of the two nucleides be equal? When will AP equals AQ? And we know that A is N lambda. We have to find lambda. What is given as T half. Fine. So, and this is also, this is not initial AP. So technically speaking, this is activity of P at time T equals activity of Q at time T. You have to be careful about some calculations here. And let's try to do this. And the relation between lambda and T half. T half is ln 2 by lambda. So lambda in terms, we can substitute for the other, right? We can have lambda. Wherever there is lambda, we can substitute ln 2 by T half. Now comes a big calculation. We have, I'm going to write P in blue, Q in some other color so that we can recognize things easily. So I'm going to write P in blue. We have N naught lambda, that is on 2 by T half of T into e power minus lambda, that is ln 2 by T half of T into time. That equals N naught ln 2 by half of Q e power minus ln 2 by T half of P into T. Be careful with the substrate. This is T half of P, T half of, so this is T half of Q. Be careful with the subscripts. You have to solve for T. Some of the things get cancelled. This is N naught lambda, N naught ln 2 gets cancelled. T is in the power. We have to take ln on both sides. On T half, T2, T half. Teacher notation. On 2, T half of P into T. So this has a negative sign, and this has a negative sign. Both can become positive. How about this side? Same thing now. Ln T half of Q minus, this is a minus, there is a minus here. So I remove minus all over this thing. Ln 2 T half of Q into T. Okay, now we need in terms of T half, the 2 and T half of P. So we have to, do some calculation. So roll with me here till here. We have to simplify this. To carefully simplify, and what is also given as half of P is 4 times T half of Q. We know the ratio. T half of Q is 1/4 of T half of P. I'm going to do this. I'll have to change this one line and kind of replace things. So what I have here is T with a common factor of on to 1 by T half of P minus 1 by T half of Q equals ln half of Q minus ln T half of P. I can write this, of course, half of Q by T half of P, ln of the entire thing. How much is this ratio? It's 4. So this is ln of 1 by 4. This is ln of 1 by 4. By erase, we cannot change it. So when I write it, if there is any typo, correct me when I write it. This is ln of 1 by 4. This T half of Q also we can write it in terms of T half of P. This is 1/4 of T half of Q. T half of P by 4. Suppose this is correct. Can I simplify and whatever we get here at this stage, at least this is simple to write. I'm going to erase all these things. So I have ln 2, 0.693, 0.693 into T, and this is to minus 3 by T half of P equals ln of 1 by 4. This is a minus 1.383. The minuses cancel. And so this divided by 3 divided by 0.693. Get it? Also, this kind of slightly went down the screen. Let me also show this just in case this is lost in correction. 6, 8, T half. At least can someone clarify, verify? But it's hard to get NAT fine, but MCQ it's hard to get that option, right? Fine, great. So many of you had difficulty with this question, and this is directly from Princeton link. So I also, when I discussed data, which year is this? In 2022, when I discussed this, I said it's from PL, and then I moved on. So I didn't give you the solution. Anyway, so now here is a solution, complete solution. All right. Okay, so far they have been only asking basic questions. New comma hash of B. This is in Tesla. This is in typically in megahertz per Tesla. So that makes this in megahertz. And we also need to know 1 Gauss is 10 power let's write it on that side. 1 Gauss 10 power minus 4 Tesla. You also need to know this. Most of the other things are kind of details. You can easily do this. Long TRUP or short TR. There is a mistake, right? Long TRUP and short TR. Only we did a long TR and a short T echo. This is PD. Not information from T2, not information from TRUP, but there will be an image. This is, if we make that correction, yeah, this is A, and notice long, short doesn't make sense. We compare it to TRUP, greater than, much greater than, T1, and then T echo much less than 2, right? Only that makes sense. Technically, this has to be partition time as T1 and then T echo time as E. Yeah, this statement makes sense. It's the reason 2024 paper had this language. Process of obtaining MRI, the terms T1 and T2 constant variables are crucial to decide on getting suitable image. Choose the correct explanation relating the two constants. T1 is spin lattice or longitudinal. No, T1 is spin lattice or longitudinal. T2 is spin transverse relaxation time. MCQ or MSQ, I don't know. So this is correct. Don't or also true statement. T1, T2 indicate durations of free induction decay. No, this is not correct. T1, T2 flipping pulses used to tell the no, we know. T1 is spin. No, again, this is correct. Basic theory definitions of T1 and T2. On. RF pulse is applied to acquire an actual MR image at the ISO center of 1.5 Tesla MRI scanner at thickness of 2, slice thickness of 2.5 mm. Assuming gradient field strength of 2 cos per centimeter, Kairomancy ratio 42.58, RF pulse bandwidth required for the slice selection. What is a del nu? So if B start of the slice magnetic field we start, let's say this is 1.5 Tesla, B end of slice, right? This is 1.5 plus gradient times distance. 1.5 plus the gradient is given to be 2 cos. So 2 into 10 power minus 4 per centimeter. The distance, so per centimeter, the distance is 0.25 centimeters. 0.25, sorry, 2.5 is 0.25 centimeters. Because this is in centimeter, I put that in centimeters. And because this is in this is in Tesla, I put this in Tesla. What are they asking for? They are asking for delta nu, that will be gamma hash delta B. Fairly easy from here, 1.5, 1.5 and all that will get cancelled. What will be left is this. Yeah, just, find this value. This is 42.58 into delta B, 1.5, 1.5 cancels into 2 into 10 power minus 4 into 0.25. How much is it? 8 into 2 into 10 power minus 4. This happens to be 0.129 10 power minus 3. But right now your answer has the units of 42.58 megahertz. So this is megahertz. Kilohertz, this will be 2.12. 10 power minus 3 and 10 power 3 will cancel, leaving you option B. So del nu is a change in precession frequency from this end of the slide to that end of the slide. That is the bandwidth, all right? And that is by definition, that's a change in frequencies. Signal depends on 2 pi gamma naught. Gamma naught is Larmor frequency. And VM, Vs, slice volume, M naught, magnitude of resulting magnetic vector at equilibrium. Alpha tip angle, BR is like magnetic field sensitivity of receive coil. Shifted to 3 Tesla machine. Initially, there is a 1 Tesla. He is shifted to 3 Tesla. That is the same amount of coil. This factor is immaterial. Slice thickness is halved. Suppose, even sine alpha doesn't change. By changing the machine, you are not changing the alpha. What will change is, of course, precession frequency will change, M naught will change. Both are proportional to P naught, magnetic field strength. Vs is also halved. What is the ratio of V2 by V1? Let's kind of write it down. V2 by V1. V2 by and all that, gamma naught. Gamma naught of this thing, it's proportional to V naught. So there will be a ratio of 3 by 1 due to gamma naught. Gamma naught to ES2, M naught 2. Other things won't matter. Gamma naught 1, VS1, M naught 1. And we know that gamma naught is proportional to B naught, the Tesla strength of the machine. We also know that magnetization is also proportional to B naught. That makes this by 1. Happens to the slice thickness. Slice thickness is halved. Slice thickness is halved. So the signal kind of like reduces. This is by 1. That gives us 4.5. 9 by 2, 4.5. Rightly, we also know that is proportional to Q. Length of the voxel, the pixel size, division. So this can also be named in terms of resolution. Dx is slice volume. It can also, technically, it can also be voxel size, right? And then this can become length of the voxel cube. And instead of slice thickness being halved, they can say length of the voxel. That's a resolution is triple, double, half, and things like that. They can easily state it that way. Pre-induction decay in the MRI of an object can be approximated as. So signal you are getting as quickly known as. So it says this is Fourier transform, 2D Fourier transform of Fourier transform, 2D Fourier transform of mx comma y. Mx comma y is the typically thing, either T1, T2, PD, whatever it is. The signal differences. And this Fourier transform will change, right? Based on M. So it affects the phase of this in a way. So how you move in the K space is determined by gradients, Gx and Gy. If you apply a Gx, it will move along Kx in the K space. That is along the X frequency, X spatial frequency. If you apply a Y gradient, it will move along Ky. That is a Y spatial frequency. If both Gy and G X are applied and they are identical and are in phase. Changing the amplitude of the pulses, one can obtain two-dimensional Fourier transform of the object or radial lines. So both X and Y are there, it will move along X and Y both. That is radial lines. Only Gx, it will move this way. Only Gy, it will move this way. Move this way in K space. Now we have Gx and Gy, Tx and Gy, it will move along this way. Of course, it can be negative GL in case it will move this way, that way, and all that. So most of that for that. And this can also be given diagrammatically, and this can also be given, the equations can be given as a pulse sequence. Description can be given as a K space trajectory. This can be given as a trajectory in K space. Instead of these options, give you 4 figures, trajectory in K space. Then this can be given as, can be instead given as pulse sequence formation. So there is one more question, I suppose. This is the last question. There is spectroscopy, maximum field of view. Kind of discussed this in bioinstrumentation, so let's not repeat it. Optics and all that. So let's just finish this one question and move on. Radiograph is 36 centimeter, 48 centimeter. Want to preserve details in spatial resolution of 6 cycles per mm. Approximate image data size is dash me. So quickly, one bit is either 0 or 1. There is a spot 0 or 1 byte bits. And then we have KB. That's 1 MB. That's 124 KB. Typically, this day we go mega, giga, tera. Tera and all is very common data science, right? Large data. But this suffices for us. Typical medical imaging purposes, you need to go to what you need to know, tera and all that, but we'll stop here. Notice if you're, this thing, if your internet power is 30 Mbps, this is small b, so 30 megabits per second. That is one thing. And then you have, notice there are something called 6 cycles per hour, something like that in that question. You need to know as 1 cycle per mm. This equals, cycle is 1 line pair per mm. 1 line pair, white line, black line. Say this is resolution printed on a sheet of paper. This will be 2 lines. Each line requires one pixel. So this also corresponds to 2 pixels. You also need to know one more thing, that is number of channels. So if the black and white is just one channel, RGB 3 channels. So if it is like 16-bit quantization, 16 bits in R, 16 bits in green, 16 bits in blue. RGB is 3 channels. So total will be 16 into 3, 48 bits per pixel. Channels. You also need to know this. Anything else? I think this is all we need to know. So given that cycles per mm, to know how many bits that corresponds to, right? So 6 in the resolution wanted is 6 cycles per mm. This is how many pixels per mm? Based on what he said, if it is 6 cycles per mm, how many pixels? 1 cycle, you need 2 pixels. 6 cycles, you need 12 pixels. I'm converting into pixels per mm required resolution because end of the day we are doing size calculations in megabyte. Be careful, it's not megabit. And then this term, so we have this in mm, so let's also convert that into mm. 360. Sir, you asked us to convert this into SI, everything into SI, and then finally into required answer, right? Sometimes for convenience, this is in mm, convert that into mm, right? Fairly easy. Mm into 480 mm. So per mm, there are 12 pixels. Per 360 mm, there are 360 into 12. On that side, there are 480 into 12, right? Total number of pixels. Let kind of write that this way. Per mm, 12 into 360 to number 10 into 10, right? Something like that. 10 row, 10 column. Like that, we have 12 into 360 into 480 into 12. If you want it slightly convenient, around 12. So per 360 mm, it's 16 to 12. Number of pixels. Is 1 pixel, how many bits? 1 pixel, you need 8 bits. We want the answer in megabyte divided by byte. So this is so many number of bits divided by, so many number of bytes at this stage. So what I had is, with that brown, I had bits. Let's divide by 8. Now we have the answer in bytes. And then we want the answer in megabytes. So let's divide this by, this is kilobyte, this is megabyte. For my satisfaction, let's calculate this. Wait, 3.7 megabytes. So the moment I had is, of course, the moment I made that correction, we have it in megabytes. This is 23.73 megabytes. Notice this is a single channel thing. Typically, black and white image. There are two channels are given, something like that. This thing will get multiplied. If there are three channels, RGB color image, external radiograph, but let's say RGB color image, that becomes 8 into 3 for channels for 24 bits per pixel. But here it's just 8 bits, one channel. So this is the answer. Please in the, of course, BM 2024. How are the medical imaging questions in the paper? Today we discuss the solutions, right? So I'll put up the solutions pretty quickly. Black and white is one channel. Yeah. But it can have many gray values. X-ray is not like, there are gray values, right? So it's 2 and 1 is like black and white. It's like 0, 0, 0, 1, 1, 0, 1, 1, right? 4 values. And then you have 8 bits, right? So is there a confusion there? There are gray values, still it's a black and white image, no? It's not like a black, gray, and white image or a gray image. It's like a black and white image. There are gray values, yeah. So we just discussed 2024 questions, right? Compared to this, similar, right? Were there any surprises in medical imaging? Half value layer? Let me recall. So this question was there. Homogeneous medium thing is there. What else? There is this question on exposure square law. Got repeated. Anything else? T2 relaxation, there is this question. Murray, there was this question. Murray, this question, right? And then they asked you for the bandwidth. They had asked for the Larmor frequency, right? Frequency is gamma hash into B. They had asked you for that, which is what I wrote, right? Or frequency is gamma hash into B. And then, if you want the frequency, this is in megahertz. If you want that in radians, you have to multiply by 2 pi, which is where we kind of use this thing. Gamma is 2 pi gamma hash. If you want the answers in radians, you can convert this in degrees, revolutions, and all that. Circular transducer. One was a new type. That question, circular ultrasound, there was a question. Ultrasound, this basic DLF question was there. But the wording again was very careful. That they had given you this question. The velocity of sound, the velocity of the blood, average velocity, maximum velocity, minimum velocity, like that. They have given the maximum Doppler shift. So they were asking for Doppler maximum velocity. So language is more precise, but essentially this question. And then there is a circular transducer from ultrasound. That question is kind of similar to this question, two scenario problem. This is very common. They had given you this ultrasound transducer, I think circular geometry or something like that. A distance r from the transducer, what is a function of pressure, right? What is a form of pressure? That was given. Then they asked you to find, ratio of pressures at two different distances. So notice, they are essentially giving you two scenarios in A, and they are giving you the formula. This is a formula. Can you apply that formula and calculate it, right? Here, at least we have to read between the lines that we have to read this information. Gamma naught is this, right? B naught square is hidden. A factor of B naught in gamma naught, a factor of B naught in M naught. That we have to read. That question, they have directly given you the formula. Can you actually put things in the same unit and calculate? Yeah, that question was new, but not a new type. It's also a two scenario question. Beer-Lambert's, again, they are going to do a two scenario question. Yeah, so the questions are predictable, at least scoreable, and that brings us end of this medical imaging discussion also. This is very, very easy, very predictable. About 8 questions per year, right? 10, 12, 13 marks you can get. So that brings us to the end of medical imaging. Next, I think we'll do engineering mathematics. I'll see if we can complete it in one part, or we have to do 2 parts. But I hope, by now, If you're watching this, you shouldn't be worrying about clearing the exam. You know all of this in and out. Videos I put in. And then you go one extra step further, right? Practice a lot of questions. PYQs are already done. If you do some practice questions that are in, say, bioinstrumentation, medical imaging, biomaterials, biomechanics, all of that is available in YouTube, right? Just by doing that, actually, you can do very well in the GATE exam.